Welcome to the lecture series on principles of electrical engineering, and in this lecture we will be trying to solve one AC circuit, basically trying to reduce that AC circuit by applying Thevenin's theorem. So let's proceed. So let me draw the circuit that we would be using to uh, uh, reduce by way of Thevenin's theorem. So there is an inductor connected in parallel to an AC source. Then it is further extended to include a capacitor. XC is here. Then there is a resistor RL. Then it is further extended, and this is R. So this R is equals to 10 kilo ohms. RL is 47 kilo ohms. 47 kilo ohms, and XC here is 10 kilo ohms. Then the voltage source is 5 angle 0 degrees, and XL is equal to 5 kilo ohms. So these are the things that have been given. So basically in Thevenin's theorem we try to reduce the circuit around two given points. We take A and B, the two given points, the two terminals, and we have to reduce this circuit to this form. Okay, so there would be a source, and it is connected in series to an impedance. Let it be called ZTH. This is VTH. Okay, and this is again the point where RL has been connected, and this is 47 kilo ohms. Okay, so this is 47 kilo ohms. Okay, so let us see how we can solve it. So basically our problem is we have basically to find out these two values, ZTH and VTH. So let us first try to find out ZTH. So the process involved is we have to remove RL from the circuit, and the second part is to replace the active sources, and we have a voltage source here, active sources, by their internal impedance. And since we are considering an ideal voltage source, so we will be replacing this source by a short circuit. Okay, so and these two steps would help us to evaluate ZTH. Okay, so basically let me redraw the circuit. Now the circuit is like this. This has been shorted here, and this is a capacitor, and this is open circuited. Okay, and there is a resistor here, R, and this is equals to 10 kilo ohms. The impedance across the capacitor is also 10 kilo ohms, and here also 10 kilo ohms. Okay, sorry, this is not 10, this is 5 kilo ohms. Okay, so this is point A, this is point B. We are interested in finding out ZTH or ZAB, which is basically ZTH. So this is equal to, just you see, this inductor, it gets shorted. See here. Okay, so we are left with this capacitor and this resistor. Okay, so they are connected in parallel when we are seeing the circuit with A and B as the terminals. Okay, so ZTH will be these two things connected in parallel. So let me write R angle is 0 degrees. Okay, and this is multiplied by XC, and XC is minus 90 degrees, divided by R minus JXC. Okay, so this is equal to, this is equal to, R is given as 10 and angle is 0 degrees. Why I'm taking 0 degrees? Because it is a resistive load. So that's why I have to use angle 0 degrees here. And then it is multiplied by 10 and the angle is minus 90 degrees because of the capacitive nature of the impedance. And then it is divided by uh, 10 minus J10. Okay, so 10 minus J10, if you write it in polar form, you will get 14.1 and angle is minus 45 degrees. Okay, while the if you multiply these two, 10 times 10 is 100 and angle remains minus 90 degrees. So finally this will lead to ZTH equals to 7.07 and angle is minus 45 degrees. So minus 90 and plus 45, minus 45 degrees. So this is the calculation for ZTH. Let us now try to find out ZTH. So let me redraw the circuit. So this is an inductor and this is the voltage source. Now this is connected to the capacitor and then so this is open circuited here, these 2 points, these are A and B, and then this is connected to this resistance R, which is equals to 10 kilo ohms. This is again 10 kilo ohms, and here it is 5 kilo ohm, and this is 5 angle 0 degrees. Okay, so so basically VTH is the voltage across AB. So VTH is equals to VAB, which is equal to VR. Okay, so consider this circuit. Let me change the color. Consider this part of the circuit. Okay, so we can apply KVL in this circuit and we can easily find out the drop across R. So the current that will be flowing, let me call it I, that will be flowing in this circuit will be given by the voltage Vs, let me call it Vs. So Vs upon sum of this and this impedance. Okay, so resistance is 10 plus then here it is not plus, sorry, it will be minus JXC. So this is the current flowing, and this has to be multiplied by again the resistance in order to find out uh, uh, the voltage across A and B. Fine. So if I write down the values, this is 10 angle 0 degrees divided by 10 minus j 10. Please remember 10 to the power 3 is also included because they are in kilo ohms. Okay, so this times 5 angle 0 degrees. So this will give you uh, it will be 50 angle 0 degrees divided by, it will be 14.14, and the angle is minus 45 degrees, and ultimately we will get 3.54, and angle is 45 degrees. So this is the voltage which we are interested in. This is the Thevenin's voltage. So basically now the Thevenin equivalent circuit is like this. So VTH, which we have calculated, ZTH, which we have calculated, and this is the resistor R of 10 kilo ohm. So ZTH we have found out. ZTH is, let me see what it is. ZTH is this much, 7.07. Angle is minus 45 degrees. Okay, so let me write it here. 7 point sorry 7.07 and angle is minus 45 degrees, and VTH we have calculated 3.54 and angle is 45 degrees. 3.54 and angle is 45 degrees. Okay, so this is how we have calculated the two values. I hope you understood the procedure involved in calculating the VTH and ZTH for the Thevenin equivalent of a given AC circuit. Thank you.